mathematics almost presupposes or premises different ideas of physics, of reality itself, right, from both a Bharatiya Gyan Parampara perspective as well as from modern science. I always say that when general relativity came about, the mathematics of that, which is differential geometry essentially, was quite advanced in the previous 50 years. Okay, so from around 1850s onwards, Larmor and various others, there was a lot of progress in the mathematics of that period. And even on the side of special relativity, when we talk about quantum aspects on the quantum physics side as well, many of the building blocks, right? I mean, in the case of general relativity and special relativity, it's the math, the of transformations, right? Minkowski transformations and differential geometry for that matter. In the case of quantum mechanics, we talk about packets, wave packets, and how discrete states can exist. I often say that there was a lot of groundwork already established in the previous 50 years. What Einstein did differently, right, was he took a plunge. Right? He took a plunge of faith, if you will, but if it was more of a scientific plunge, and he took the idea forward, saying that this is actually a very good language, right, to talk about gravity. This differential geometry actually talks about gravity in a certain context, and there is a reason. I mean, there's a whole physical reason how he got to that point. But he said that gravity is no longer something which is a force. Right? Gravity is something which is more of a curvature in space and time. Right? So if you can think of space-time as a tarpaulin sheet, as it is often mentioned, and you put a small marble ball on it, the curvature that happens is basically the effect of gravity. Because if you now put a small, let's say, lead bearing, there is a smaller ball, let's say metallic ball, and you pass it, let it roll on the tarpaulin sheet, as soon as it goes near that curvature, it will kind of move around it, it will circle it almost, right? So you can think of curvature and gravity from that perspective. So clearly the mathematics presupposed the physics of it. So in the Bharatiya Gyan Parampara, we also see a resonance of that kind, right? You just now mentioned Bodhayan, right? I mean, we should actually stop calling it the Pythagoras theorem, right? We should start calling it as Bodhayan theorem, right? And the work of Indian mathematicians for determining pi is very, very important, right? So for instance, in the Shatpat Brahman, we find the first mention of a way to talk about pi with the value often cited as 3.139. Aryabhatta, he kind of gave this value at 3.1416. Madhava of Sangama grammar later on gave a value up to 11 decimal places, right? He said 3.141, 592, 653, 59, right? So that level of precision, right? And because pi is very important for any kind of circular dynamics, circular aspects, right? And invariably, if we talk about orbits, if we talk about the way things are rotating or revolving, there was a lot of translation of that into talking about planetary motion as well, these understandings, so to say, right? And when we talk about the treatment of planetary revolution, the way they looked at the circular mechanics, of course, as well as sine tables and trigonometric calculations is also very important to consider, right? So Aryabhatta gave a very systematic way, right? And it almost looks like, we often say Newton, right, was a genius because he looked at calculus, he looked at mechanics, and he looked at gravity, right? And they were all connected, because when you talk about infinitesimal change in position, let's say, in mechanics, you have to connect it to the differential, the concept of the differential, right? Similarly, Aryabhatta also looked at the intricate connections of the mathematics he developed, as well as the planetary motion, that talk of planetary motion that he had looked at, essentially, right? So I mean, his geocentric model, though, right, was later on looked at from a more heliocentric aspect. But the idea of relative motion and periodicity, right, is something that was very, very important in that way. Now, let us move forward to Brahmagupta, right, who gave the treatise Brahmasfuta Siddhanta, right. In that, he talks about fundamental concepts of zero as well as the concept of negative numbers, right, which were very revolutionary when we talk about mathematical operations, so to say, right. And so when we talk about Newtonian mechanics, right, and when we talk about relativistic physics also, the way in which we define singularities, we define constructs of negative numbers as well. Like for instance, in Minkowski space, the metric, we talk about the metric, it is often with a minus sign that the time aspect is given with respect to the spatial aspect, so to say, right, minus Ct x, y, z, right. So the negative numbers aspect of things is very important to define anything on the front of mechanics, on the front of orbits, or any astronomical calculations as well. Now, in the case of Brahmagupta, it didn't quite translate directly. I mean, he didn't work on many aspects of planetary motion per se, but his work was important in derivative works, in further work, so to say, right. Now, Bhaskara too, right, in the Siddhanta Shiromani, right, he spoke about Tatkalika Gati. Tatkalika Gati means instantaneous motion, basically. And when we talk about Tatkalika Gati, we have to basically talk about the concept of derivative in a way, right, because you're talking about the instantaneous motion, not a motion over a certain period of time. So we see there is a certain understanding of how the motion is tracked and determined for a certain instant in time, right. He obviously had a use of various small increments of the algebraic and the trigonometric side also, so to say, and which was very important in the Kerala school. We often talk about the Kerala school of mathematics, right. This was very, very important in that respect, right. Now, Bhaskara too also had a very important role to play in the Kutaka method. Kutaka method basically was to solve, it was a method based on fractions to solve indeterminate equations of the form ax plus by is equal to c. Okay, and they are basically called the Diophantine equations. These are called Diophantine equations, and it was used for this kind of an equation, so to say, right. Now, this was very important because when you do recursive planetary calculations, right, when you are doing basically things like even eclipse corrections, there are many such techniques, right, which can be applicable or which are applicable in various ways, which has a premise on these numerical methods or these methods of algebra which were developed back in the day as well, right. So, but you may ask whether it directly translated to the works of the Western philosophers and mathematicians or astronomers. I mean, there are debates on that, right, because there was a lot of civilizational flux that was happening, right. We also, many people say that our algebraic aspect or mathematical aspects went to the Middle East, right. Today we call it algebra from al-jabr, right. But the motivations of that, right, the origin points of that is a whole different debate altogether, right. And how that further led to influences into the Hellenistic or post-Hellenistic world in the European traditions is again a matter of debate, right. But I like to believe that because we have had a long history of very precise applications of mathematical concepts, right. We were discussing about the Sulba Sutra, right, whether how the altars were prepared and the geometry of that. It shows a very advanced method or understanding of the geometries of altars and how the applications of tiling or tessellation, as it is called, right. There is a beautiful constructions which are having very different kinds of geometric units that come together beautifully, right. So tessellation is a part that comes into the picture. So definitely there was a lot of advancement on that front, right. Now, when we talk about the intricate link between the two, right, and that is what I would like to highlight here. It was not from Newtonian or post-Newtonian, but I would say pre-Newtonian physics, yes, right, from the Bharatiya Gyan Parampara, where we see this simultaneous development of the mathematics and the astronomy, so to say, right, and the application that was synchronized, right. It was going hand to hand, it was going together, right, and till we appreciate that, we cannot understand the enormity of this, right. And that's why I started with this whole contextualization that Einstein's relativity would have been nowhere if differential geometry was not advanced as it was, right, because everything from the Ricci tensor to the curvature aspect, right, to how we define the stress tensors and the transformations thereof, right, covariance, contravariance, so on and so forth, right, translation in certain manifolds. These are all things that came from differential geometry that translated into Einstein's relativity, general relativity. So similarly, because of Aryabhatta's work, because of Brahmagupta's work, because of Bhaskara II's work, and their synchronized corrections in astronomy, their applications, we would not have reached where we were, right. And be it prakarana, be it the other declination based aspects, be it frame dependent aspects, these are all things that show us that we did have a lot of understanding of the contextual mathematical advancements and their specific applications in the astronomical tradition, so to say.